Hello, everyone. This video is a follow-up to my second book, State Capitals and the Distance Between Them, which was published in 2019 and is available in Amazon. Today, we're going to take a look at not the distance between state capitals, but the distance between our national parks. We're going to start that journey here by considering the fact that there are 63 national parks in the United States. Today, we're going to embark on a journey between parks over time and distance. The year is 1872. On March the 1st of that year, President Ulysses S. Grant approved our first national park, Yellowstone National Park. Now we're going to pick a point in that park. We're going to look at the Old Faithful Visitor Center, which is located at approximately 44 degrees, 27 minutes, 30 seconds north, 110 degrees, 49 minutes, 46 seconds west. We're going to call that point A. Now, again, we're going through time. And we're going to fast forward to the year 1890. On September the 25th of that year, President Benjamin Harrison established Sequoia National Park in California. The Foothills Visitor Center is found at approximately these coordinates. Again, you can see the degrees, minutes, and seconds. Keep in mind that there is 60 seconds in 1 minute and 60 minutes in 1 degree. So very similar to the clock. We're going to call this point B. When we think about north, north means it's 36 degrees, 29 minutes, 28 seconds north of the equator. And just for reference, the North Pole is 90 degrees north of the equator. Now, with regards to west, we're talking about the number of degrees west of the prime meridian, which runs through England. We're going to call that point B. A third point on our illustration is going to be designated as the North Pole in this video and subsequent videos. So here is our spherical triangle. Now note that I have the word spherical in quotes there. We're taking a look at points on the Earth. The Earth is not a perfect sphere, which is okay. It's approximately spherical. We're going to use that to our advantage to find some nice calculations. The average radius of the Earth is 3,959 miles. Now, the radius is a little bit greater at the equator, less at the poles. But again, that's just an average, and that's going to work quite well in our calculations. We're going to use that value later on, actually. To calculate our distance, we are going to use the spherical law of cosines for sides, which is the same formula that I use in my previous books, both the one in 2017, approximating distances between rolled capitals, and the one that I showed you earlier, which was published in 2019. Now notice here that we have the cosine of C, and C is the side of our spherical triangle that is opposite angle C. Now, angle C, capital C, that's at the North Pole, and that is the length of the side opposite that. Now, we think of this both as a length, but also as an angle itself. And the same thing could be said about the lowercase a, the lowercase b as well. Notice that's a capital C. All the rest of the letters are lowercase. So we're going to revisit our illustration of our spherical triangle. Let's take a look at this once again. And here we have the North Pole. Little c is opposite, capital C. Little a, opposite, capital A. Remember, capital A, that is our visitor center in Yellowstone National Park. And little b, side B is opposite, capital B, which is our visitor center in Sequoia National Park. What we are looking for here is this. We want to calculate the value of C. We want to find this in miles. Now we're going to find it first in degrees, but then we're going to find it in miles using another formula. And before we get too far, we're going to make a conversion here. I gave you the angle measurements in degrees, minutes, and seconds. We're going to convert those to the degree decimal form. So point A, that's point A. We have 44 degrees, 27 minutes, 30 seconds north. So what I do is I have 40 plus 27 over 60. After all, there's 60 minutes in a degree, and there's 60 seconds in 1 minute, but 60 times 60 is 3,600. So we take this 30 divided by 3,600. We add all these together. Do this on your calculator. I'm going to round all of these to 4 decimal places. You can round to more or less decimal places if you like, and you could have a whole discussion about approximate values and significant digit, but you can do that on your own if you like, but we're going to stick with 4 here, and we're going to find we get some really nice values. So that is degrees north. And notice I do the same thing with all the other calculations. And feel free to pause this video as needed to take a look at these in more detail, but I convert all 3 of the other ones to degree decimal form. All right, so we're going to look at our picture once again. Back to the triangle. What do we know so far? We know, well, we want to find this angle C up here. We want to find this angle C as well. Again, they're both angles, which can be confusing. One's a lowercase c, that's its side. One is this angle, capital C, which is this. Here is angle B. Here is side B. Here is, again, angle A. Here is side A, which is also an angle. But notice I have all of these angles now in degree decimal form, both the latitude and the longitude. Latitude goes north to south. Longitudes go east from the east to the west as well. So, well, A, B, and C are sides. They are also angles on great circles. Now, what is a great circle, you may ask? Well, imagine you have a sphere, like a basketball, for example. Imagine you have a plane, like a piece of paper. And imagine, if you will, that you can take that piece of paper and you can slide it right through the basketball. The basketball doesn't deflate. You can see where the two intersect. You can also take a look at graphing these using things like Desmos or GeoGebra, graph circles and spheres and see how they intersect. So again, great circles are formed by the intersection of a plane passing through the center of a sphere, has to pass through the center of the sphere and the sphere itself. So let's go ahead and find those angles A, B, and C. Notice again the lowercase and the uppercase distinction here. To find out what A is, we take 90 degrees, we subtract its latitude, which is 36.4911 degrees, and we get this. That is the measure in degrees of side A, which again is opposite angle A, capital A. We find B in a similar way. And then C, how do we find C? Well, these use the latitude. This is the difference of the longitudes. Notice I have the greater value minus the lesser value. We could look at the absolute value of the difference here. We could take this value minus this, look at the absolute value. Either way, we get to this angle measurement of 7.9962. Now, notice this illustration that I have. It is not drawn to scale. It is merely a rough sketch. So we're not going for artistic quality here or exactness. We're just looking at a rough sketch to start with as kind of a baseline for everything that follows. So actually, this could be much more narrow if we were to think of this in an exact sense. But this is C. We want to find out what this is. We now know what this angle is. We now know what little b is. And again, always keep in mind your goal. What we want to find is C. So let's look at our formula again with our values. Since C is our only unknown value, we have the following. We have the cosine of little c is the cosine of A times the cosine of B plus the sine of A times the sine of B times the cosine of angle C that we have up here. And make sure, put that word in there. Make sure your calculator is in degree mode, not radian mode. We're going to talk about radians later, but needs to be in degree mode for now. So if you look at all the calculations, and you might want to do it a couple times just to check your work, we find that the cosine of little c is approximately this. Now we could have a whole video talking about, again, significant digits and rounding and all that fun stuff, but we're just going to take it out all the way that we see in our calculator. Those are all the digits it gives me at least. And then C is equal to the inverse. That's the inverse cosine of this value. So I apply the inverse cosine to both sides. Now, I would suggest if you have it at trig to review things like sine and cosine, inverse sine, inverse cosine as well would be good. You don't have to go through too many things at trig, but just a few basic concepts, and that should lay the foundation for everything we're doing here. And those concepts are also talked about in my previous two books. So C, again, I'm in degree mode. It's this number of degrees, just a little bit more than 10 degrees. But again, we don't want to know what C is in terms of degrees, but we want to measure in miles. So to calculate our final answer, we use yet another formula, the arc length formula, which is S, the arc. So when you think about an arc, think about a circle here. And think about a circle of radius R. So it's going to come out here. That's R. This is R as well. So what is an arc? That is a distance from here all the way around to this point. So from this point all the way around the outside of the circle to this point, that's that distance. Now, the one thing is that theta, as we'll see here, theta is going to be in radians this time. But before we get there, recall that I earlier mentioned that R is approximately, the squiggly signs means approximately equal to 3,959 miles. But as for that theta, I should say, in the formula, it is an angle, but in radians, it has to be an angle in radians, not degrees. So we must convert our value of C to radians. So what we have is this. There's my R value, and then I have the angle of degrees. How do we convert from degrees to radians? We multiply by pi over 180 degrees. Now remember, pi is a very special irrational number. It's approximately 3.14159, but that's only an approximation. Actually, the decimal part goes on forever, never repeats, never terminates. That's, again, what we call an irrational number. Now, the distance from The one visitor center to the other one is approximately 691.87 miles. And when you think about that distance, that is not the distance that you would travel if you were to, say, get in a car and travel from the one visitor center to the other. Because to travel from the one point to the other, you're not going to take a straight path over the arc of a great circle to get from one location to the other. You're going to go on roads and you're going to kind of or zigzag, I should say, to get from point A to point B, and it's going to be much greater than that. But imagine, if you will, that you were flying an airplane and you were starting at the one visitor center and flying directly to the other one. It would be approximately that distance, is what I'm saying. So I hope you enjoyed the video. We'll take a look at going from Sequoia National Park to our next park, our third oldest national park in the next video.